Hello everyone. Welcome to this RSET training on monitoring and modeling floods using Earth observations. My name is Amita Mehta and I will be conducting this introductory training with the help of my colleague Sean McCartney. Today we have a guest speaker also, Caroline Williams from NASA Develop. Overall training objectives are as follows. By the end of this training, you will be able to identify observation-based flood monitoring and mapping tools, identify selected open source flood models, and understand and plan for using hydrologic and flood routing modeling techniques for your own use. There are several prerequisites. These three webinars shown here from RSET, they provide information about fundamentals of remote sensing, about NASA's Earth observing satellites and sensors, and remote sensing for water resources management. All three webinars have information that helps in following the current webinar and makes it easier. More importantly, this link provides RSET advanced training that we conducted a couple of years ago, and that focused on observational based flood monitoring techniques and tools. So some of the tools that we will mention here are described here in detail in this advanced training. Not only that, there are some hands-on case studies that you can work through to use these flood monitoring tools. So we will not repeat those exercises, or we will not go through details of those flooding tools. What we will do is talk about some of the tools which are upgraded since then, or things have changed, and then focus more on newer flood monitoring tool that has come up, and then focus more or review more about flood modeling. So that is going to be the goal of this training. There will be two 2-hour sessions, including question and answer session at the end. They are provided in English, but materials are available in Spanish from RSET website. Today we will focus on overview of flood monitoring and modeling techniques and some tools. Then next week we will have specific example of the hydrological modeling and analysis platform HYMAP with some case studies. Outline for today is that we will have a brief introduction to RSET for those of you who are new. Then we will have flood monitoring tools based on remote sensing overview. We'll have overview of selected flood models. We'll also demonstrate websites for the remote sensing based flood tools and selected flood models. More importantly, we will introduce a new observation-based flooding tools, the hydrologic remote sensing analysis for floods, or hydrofloods. So Caroline will be talking about hydrofloods. There will be one homework assignment that must be submitted via Google form and can be accessed from RSET website. It will be posted on 21st of September, on the last day of the webinar, and it will be due by 7th October. A certificate of completion will be awarded to those who attend both these live webinar sessions, complete the homework assignment by the deadline, and then a certificate will be awarded approximately 2 months after the course is over by Marinus Martins. So we'll start with an introduction to RSET. Applied Remote Sensing Training Program, or RSET, is part of NASA's Applied Sciences Capacity Building Program, and it aims to empower global community through online and in-person trainings that focuses on use of remote sensing in water resources management, or air quality monitoring and management, land management, and disasters. Also, there is a newly added topic on climate, and we already had a training related to introduction of climate change, and there will be subsequent webinars coming up too. RSET's goal is to increase the use of earth science, remote sensing, and model data in decision making through training for professionals in the public and private sector, environmental managers, and policymakers. Please note that all RSET materials are freely available to use, either in your curriculum in your classroom or for your own applications. If you use the methods and data presented in RSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. So we'll start with today's topic on flood monitoring tools based on remote sensing. Before we do that, floods, as we know, it's a temporary overflow of water into land that is normally dry. Important thing to note is that number of floods are increasing, as this Relief Web report showed. In 2021, flood numbers increased to 223 from average 163 annual occurrence based on this 20-year period, 2001 to 2020. Overall, there were 432 catastrophic events in 2021, and floods dominated these events. We know that it's the most common disaster affecting human lives. It can cause infrastructure damage and power outages, disrupt transportation, create landslides, and just to put things in perspective, about 6 inches or 15 centimeter of moving water can knock a person down. It's that much force, and 1 foot or 30 centimeter of moving water can sweep a vehicle away. So it is a very powerful and devastating disaster. And therefore, flood monitoring and management are very important. As described in this Urban Flood webinar by RSET, there are requirements for effective flood monitoring and management. They include both geophysical and socioeconomic data listed here, including, say, terrain and digital elevation modeling for floodplain mapping, information about low-lying areas, regional precipitation intensity and frequency, river stage, stream flow and inundation, coastal surges and inundation for coastal regions, of course, land use change, including exposed soil versus built-up areas and soil moisture amount. Also, socioeconomic data such as population, infrastructure, drainage, and stormwater system capacity, especially for urban flooding. These are all very important for effective management. Also, statistical information based on past data that tells about flood return period that also helps in effective management of flood and its impact. Hydrology and routing models, they not only help in monitoring and management in real time, but they can also be used in forecast mode or predictive mode for flood management. So flood extent and flood intensity can be predicted using these models. And we will talk about that in this webinar. Reviewing the observation-based flood detection, there are a number of techniques or several approaches as listed here. First is detecting floodwater on previously dry land using satellite-derived land cover observations. And for that, optical satellite data as well as microwave radar data are commonly used and for looking at land cover and detecting floods. Another approach is to use hydrologic model and derive stream flow and runoff using precipitation and weather data from satellites and models as inputs. Third approach is purely statistical model or methodology, which infers flooding based on satellite-derived precipitation rates and amount and soil moisture. So it's just statistical technique that tells you about flood occurrence. Also note that all these approaches, they do use some kind of modeling and surface-based observation data in addition to remote sensing. So altogether, they provide best monitoring and mapping capability, also using model that can be prediction. Statistical techniques are sometimes used for prediction as well. This is the list of open source flood monitoring tools based on remote sensing. The first three tools, Moody's-based flood mapping, Dartmouth Flood Observatory or DFO, Global Disaster Alert and Coordination System or GDAX. These three have been around for a long time, and ARSAT trainings have covered all these three tools in detail, and the links are provided here. Advanced Rapid Imaging and Analysis tool ARIA, that is a newer tool, and HydroFloods, we already talked about, that's a new tool as well. So what we will do is talk briefly of what has changed in these three tools, briefly talk about ARIA, and focus more on HydroFloods, where Caroline is going to walk us through a case study, and so that helps us see how this model or this tool can be adapted for our own region for flood monitoring based on observations. So let us first visit Moody's-based flood mapping. Earlier, we used this website for looking at Moody's-based flood maps. This site is no longer working. All the near real-time or current flooding data are available from NASA Worldview. If you want to look at past flooding events, starting from 2002 onwards to about 2021, you can still use this site, but there is a better visualization in NASA Worldview. So let's briefly look at how we can see Moody's-based flood maps from Worldview. And as we've talked in earlier trainings, Moody's uses optical reflectances to detect water when it comes over dry surface. So that change is detected, and that's how flood is mapped. So let's look at NASA Worldview and look at Moody's flooding. If you go to NASA Worldview, you will get this window. You can take the tour. Here you can search for different layers. So let's search for flooding or flood, and it comes up with a number of choices. These two are Moody's-based flooding. This is 2-day composite and this is 3-day composite. So let's look at 3-day composite. And once you select that layer gets added to this. So this is Moody's flood map. You can also have place labels, turn them on, and coastline and borders. So let us look at some recent floods. We know that Pakistan had devastating flood very recently, end of August to early September. So this is the timeline, and you can pick days, or even you can change months if you like. But let's look at the recent flooding. These, if you look at the legend here, blue is the surface water, red is the flood water, and the gray areas are where either there are clouds or there are no data available. But even when there are data missing, you can see this flooding in Pakistan in large regions actually. You can go back and you can see how flood changes. The area of flood extent, it's changing. So this is early September when actually flooding was very, very high. So these are orbit gaps. These are clouds. Because of that, you can't see the surface in optical data, but wherever there are clear skies, you can see flood map. So this is a better visualization than the earlier website, and you get the same information here. You can also add other layers such as, say, precipitation, and you can say precipitation rate. iMerge is from GPM. If you add that, you can see there is heavy rain here. There is rain rate given, and you can see that where there is flooding upstream of this river, there is rain. And so this worldview actually allows you to look at multiple parameters along with flooding. You can also look at soil moisture along with this. You can look at land cover also. So this is one advantage of looking at Moody's based flooding in worldview rather than the our old website. The next one is Dartmouth Flood Observatory. So right now there are no global map of near real-time flood on DFO, but there is a river watch facility. It's based on passive microwave observations and river gauge measurements. So at locations on rivers where there are river gauge measurements available, a technique is developed so that based on microwave radiometer data and stream gauge data, stream flow can be derived at these locations based on satellite data. This technique is currently being revised and also is being validated. So RiverWatch also is not near real time. There is some latency, but that information is available from the observatory. And let's just look at the website briefly. If you go to the DFO website, you will see some flood maps. This one is for Kentucky flooding in 2022. These maps are based on SAR observations. It shows where there was heavy flooding going on. But the current flooding that used to be available here, based on Moody's again, that has been halted. But RiverWatch, which is under revision, it is still available. And let's again go back to our Pakistan flood case and see if we can see that. So if we go here and click here, this is Indus River, Pakistan. This is 7th September is the last measurements, and this is discharge in cubic meters per second. This is derived from microwave radiometry. So this is from January 21. The time series is shown here. This is late August to early September is where there is this flood spike in Pakistan that we can see here in the discharge derived from microwave data. Similarly, this is the long time series starting in 98 January, and it is not current, but it has some latency, but this is when there is major flood going on, you will be able to see this river gauge data and discharge information. It shows annual runoff, mean over the entire period, and it also shows the monthly runoff for the same period. In addition to the current flood, this is also well-known 2010 flood that you can see in the runoff. So this is a useful facility to look at stream flow on DFO. The third one is GDAX. GDAX interface has changed compared to our earlier GDAX training, but the same information is available about multiple hazards, as you can see here: earthquake, tropical cyclones, floods, volcanoes, droughts, and forest fires. So GDAX combines local data, in situ data, socioeconomic data, and damage data collected in situ by a variety of sources, as well as satellite data and modeling data from a number of institutions. Whatever data are available for a particular disaster, they're collected and they are made available for an integrated overview of the disaster. So this is a useful site, especially to look at particular events here. And so let us look at this site, GDAX site, and look at flood cases or flood events. So this is the homepage for GDAX. When you go down, you can see different disasters. There is current flood going on in India and Nepal and Mexico, which is low intensity because it's green color. Medium is orange and high is red. So again, you can click on this Pakistan flood that we've been looking at. This is in August, I think 31st of August. So this is a long period coverage here, and you can look at information about this particular flooding. There is SAR-based flood detection available, and if you look at maps and other resources, here is a satellite detected water extent. This is from NOAA WEIRS data, and you can see the map here that's showing water extent. If you look at this map, this is as of 15th August, again shows surface water. This is based on Sentinel-1 SAR data. So there is a lot of information available about a particular disaster when you go to GDAX. You can look at, this is again yet another satellite picture from WEIRS that shows water extent. You can look at exposure and preliminary impact estimates for this event, damage assessment. So as it becomes available, it is added to the website. So this is also a useful website to monitor and track flooding and other disasters. Finally, we come to the newer tools. We will briefly look at ARIA and then go right to Hydra floods. And then we will have demonstration from Caroline about Hydra floods. So let's start with ARIA. So let us first talk about ARIA. It's a collaboration between NASA Jet Propulsion Laboratory and California Institute of Technology. ARIA uses satellite data from SAR sensors, also from optical sensors, uses global positioning satellite data and seismic observations for looking at multiple natural hazards, particularly processing impacts related to hazards. Although primary focus of ARIA is ground deformation chain measurements, it also includes flood damage proxy maps. If you go to the ARIA website, you will see products overview. And if you go to urgent response products, flood proxy maps are available there. And when you go to those maps, you can find flood cases seen by satellites. Here is an example for Kentucky flooding in 2022. All the shaded region in yellow, orange, and red, they show surface water or flood water in this region. If you look at this link, that's an ARSET webinar that also shows how to use SAR data to detect flood water. And this also uses ARIA, uses similar technique. It also combines other data in there. So let's just briefly look at the ARIA website and see where to get flood proxy maps. So this is the website. You can get information about this, but here's the products link. Once you go there, we have flood proxy maps here.
So this is based from Sentinel-SAR, so it starts in 2014 and it goes up to 2022. This is the Kentucky flooding map that we just saw. Let's look at one more case. So these are all different cases seen by that SAR satellite. Let's look at this Australia floods. If you click on that, it will show the satellite overpass where floods detected. Let's look at this KMZ file. Although you can see different formats, there's a it's in zip shapefile format. It's available. Let's look at this KMZ. So KMZ file you can look with Google Earth. And so let's look at the flood case over Australia. It is taking a minute to open this site. And here is where Australia 2021 March, you can see where there is flood water on the surface, where there is water. So you clearly see this flood map here. So ARIA provides flooding information based again on optical and SAR. And the final tool that we're talking about, HydroFlood, that also uses multiple data sets from satellites, SAR as well as optical. So now let's look at HydroFloods.
So now let's look at HydroFloods. HydroFloods is developed by Surveyor, that is NASA and USAID Surveyor program in collaboration with ADPC, which is Asian Disaster Preparedness Center. So HydroFlood is a publicly available web-based near real-time flood monitoring tool, and it is developed specifically for emergency response and relief sectors. It uses open source satellite data from optical and synthetic aperture radar sensors, and also importantly, it is developed using Google Earth Engine and Google Cloud Platform with Python API. Currently, it is available for Mekong River Basin, but the code is available and Python API is also available so that one can use it for the region of your interest. HydroFloods uses a number of satellites, Sentinel-1 C-band SAR, Sentinel-2 optical data, Landsat 7 and 8, WIRS and MODIS optical data. So with quite a few satellites, it has good temporal and spatial coverage for flood monitoring. We will look at the website, but algorithms are described here, and HydroFlood, it allows access to high quality cloud-based surface water mapping algorithms. It has algorithms for SAR image correction like speckle filtering, then terrain correction algorithm, that is for optical imagery, there is illumination correction, and it generates water map based on data, and the algorithms are available. So let us see. This is the website. It is the map viewer, and let us look at the site. So this is the HydroFloods viewer from Surveyor. Right now it is focused on Mekong Basin. You can go to map viewer. It takes you to the Mekong Basin. This is quite recent. This is September 11, 2022. And what you see here is flooded water based on SAR alone, flooded water based on optical data, based on combined optical and SAR, there is seasonal and permanent water data as well. So if you zoom in, you can see that here is where there is flooding. There is seasonal water, and then dark blue is the permanent water. So dark blue is the permanent water, light blue is the seasonal water, and these are the flooded regions. So right now this is available for Mekong Basin, and Caroline will show us a case over Central America. There are use cases. This is over Thailand, and it shows, this is September 2021. It shows the flood extent or flood map, again based on SAR and optical data. This is flooding in Cambodia. So clearly it shows where there is flooding going on. Again, this is permanent water. You can look at user material. It has methods and documentation. GitHub repository is there, and user manual is there. So you can look at the user manual, and it tells you how to install this Python API and how to use Google Earth Engine along with Google Cloud to work with hydrofloods. So you can look at this information if you want to use this tool for your own region. So now I want to invite Caroline Williams for her presentation, and she will be showing us application of hydrofloods. And Caroline is a member of NASA Develop team. NASA Develop program is sister program of ARSET, working on capacity building. So after Caroline's presentation, we will conclude these observation-based flood monitoring tools, and then remaining time we will spend on overview of flood models. So after Caroline's talk, we will resume our presentation. Here I invite Caroline. Please take it away. Thanks.
Hello, I am looking forward to diving into the application of the NASA Surveyor Hydrologic Remote Sensing Analysis for Floods, or HydroFloods tool, presented by a case study analysis conducted via a recent NASA developed project at the Marshall Space Flight Center node or location in the fall of 2021. My name is Caroline Williams, and I'm a fellow with the NASA Develop program managing projects at our pop-up project locations. The Central America Disasters Project that I'll be presenting here focused on using Earth observations to map flooding for disasters monitoring to inform potential risk and prepare for possible response. In this project, we examine the flood impacts of Hurricanes Eta and Iota, as well as produce historical surface water maps, precipitation maps, and a code tutorial for the Central American region. Although we utilize hydrofloods for producing the historical surface water maps for the study area, I'll be highlighting the application of the tool through the case study analysis, examining the extent and impact of flood from these two devastating back-to-back events. By the end of this case study overview, I hope you'll be better informed on how to utilize hydrofloods in your flood monitoring analyses. Before we jump in, I'd also like to acknowledge my fellow team members on the project, including Lauren Carey, Maria de los Santos, Deanna Finelli, and Payne Ireland. As we begin to think about the tools and technologies available to facilitate flood monitoring efforts, it's important to recognize the impact of these communities and how using Earth observations and flood detection algorithms can address some of these concerns. On November 3rd, 2020, Hurricane Eta made landfall in Central America, and just 2 weeks later, on November 16th, Hurricane Iota followed a similar path. These storms brought catastrophic wind and rain to the region, affecting more than 8 million people. Combined, these storms caused an estimated $738 million in damages and 189 deaths. With the increasing frequency of these storms, it is crucial to understand how flooding has affected communities in Central America in an effort to better prepare for future events. With these concerns in mind, we partnered with 3 organizations, the first being the Sistema de la Integración Centroamericana, or the Central American Integration System, and they coordinate economic and political activities between Central American countries since 1993. And the administrative center of SICA is based in El Salvador. We also partnered with the Comité Regional de Recursos Hidráulicos, or the Regional Water Resource Committee, and they're an intergovernmental body under SICA that focuses on water resource management, specifically by coordinating and facilitating projects and working to strengthen national water management policies. And lastly, we also partnered with the Centro de Coordinación para la Prevención de los Desastres en América Central y República Dominicana, or the Coordination Center for the Prevention of Disasters in Central America and the Dominican Republic. And they are also an intergovernmental body under SICA, and they promote international cooperation and exchange of information and technical support in disaster prevention, response, and mitigation. In our project, we examined numerous countries in Central America. While we examined all countries for the historical surface water maps, in the case study analysis, we focused on countries most impacted by the 2 events. This includes Guatemala, Honduras, Nicaragua, and El Salvador. Similarly, the study period also varied by each analysis. For the case study, we focused on October 17th through December 2nd, 2020 to highlight flooding during both events and the flood impact the following weeks after the hurricanes passed. To help identify impact and decide where to prioritize a case study analysis, we generated precipitation maps for each hurricane event by looking at total precipitation. Similar areas across the region were impacted by heavy rainfall, specifically the coastal areas of Honduras and Nicaragua facing the Atlantic were exposed to the highest amounts of precipitation from these 2 hurricanes. This, along with partner input, helped identify which countries to prioritize in conducting the flood case study analysis utilizing the HydroFloods tool. Expanding on the spatial distribution of precipitation, we also looked at precipitation by day for each country that we examined in the region. As you can see in this figure, hurricanes Eta and Iota are delineated as well. For both hurricane events, we saw a peak in precipitation, most notably countries like Guatemala in this green line color, Honduras in gray, and Nicaragua in brown experienced some of the greatest amounts of precipitation concentrated over just a few short days during each hurricane event. Again, this information helped identify key countries to look at for flooding. This precipitation analysis can help identify study areas to look at for flood impacts and can act as a preliminary analysis before implementing the HydroFloods tool. With all this information in mind, we set out 3 key objectives, one of which we'll focus on for this overview of the application of HydroFloods. For our goal was to identify areas vulnerable to flooding by producing surface water and precipitation maps. Second, we conducted a case study analysis of hurricanes Eta and Iota to demonstrate the applicability of HydroFloods for disaster monitoring in the region. Lastly, we generated a step-by-step guide to support our partners in replicating the steps performed in our analysis using HydroFloods. For today's discussion, we'll primarily be focusing on the case study analysis to demonstrate the application of HydroFloods. When working with HydroFloods, there are many optical and SAR satellites and sensors available for use. This helps provide the user several options when examining flooding for their study area. In our project, we utilized a variety of optical satellites and sensors, including Landsat 8 Operational Land Imager, or OLI, Landsat 7 Enhanced Thematic Mapper, plus Sentinel-2 Multispectral Instrument, SOMI National Polar Orbiting Partnership, Visible Infrared Imaging Radiometer, and Terra Moderate Resolution Imaging Spectroradiometer for surface reflectance. And mapping flooding using optical imagery can have its challenges, particularly with the temporal resolution and likelihood of cloud cover. For instance, when examining flooding derived from hurricane events, the ability to view the degree of flood extent depends on when the satellite is revisiting the area you're looking at. There could be instances where flood extent was greater than what could be captured, and there's also an issue with cloud cover since hurricanes are inherently cloudy, so much of the image will be covered and inhibit the user from viewing certain areas of flood impact. So having numerous optical Earth observations at our disposal helps to reduce these limitations. In addition to viewing optical imagery, we also utilize Sentinel-1 C-band SAR, or synthetic aperture radar, for measuring backscatter. SAR is incredibly useful for detecting floods from hurricanes due to its ability to penetrate clouds, unlike optical imagery. Although it's important to note that SAR comes with its limitations as well for flood detection. Primarily urban land cover types can be detected as flooding when it's not. And with these factors in mind, we demonstrated all Earth observations, so optical and SAR, in our case study analysis. Lastly, we also used Shuttle Radar Topography Mission, which is an SRTM-based products like Merit Hydro for elevation, which was used in our pre-processing analyses. Before diving into our methods, HydroFloods, or the Hydrologic Remote Sensing Analysis or FLOODS tool, is a Google Earth Engine-based tool operated using the Python API. Our scripts are written in Google Colab, which is an environment which the user can write and execute Python code in their web browsers. Although we used Google Colab, HydroFloods can be used on local Python scripts or in other environments. This workflow diagram is split up by Earth observations, pre-processing, analysis, and outputs, as you can see, row by row. Looking at Earth observations, we used optical, SAR, and Merit Hydro, along with ancillary data sets like CHIRPS for precipitation and ESA World Cover 10 meters, version 100 data set for land cover. Focusing on data pre-processing, the approaches used here differed for optical and SAR before using one of the key flood detection algorithms that's offered in the HydroFloods tool. For optical preprocessing, we first filtered the imagery by our study area and period. HydroFloods also automatically masks cloud when importing these Earth observations into the script. And since we looked at a relatively large study area, we then mosaicked the imagery. And following this, we calculated the Modified Normalized Difference Water Index, or MNDWI. MNDWI uses the green and shortwave infrared, or SWIR bands, to enhance the visualization of open water features and removing noise from built-up land cover types. So calculating MNDWI helps prepare the optical imagery for the thresholding analysis that follows. And going into the pre-processing for SAR, we also filtered the data by study area and period. But differing from optical, we then performed a pseudo-terrain flattening algorithm and speckle filtering analysis. This was followed by implementing an elevation mask for areas greater than 20 meters above the closest water body in the study area. And these pre-processing steps with SAR helped to remove the likelihood that shadows from high elevation would be falsely detected as flood in the main analysis. Although the data processing differed between SAR and optical imagery, we applied the same methods to extract flooding information. Using the HydroFloods tool, we implemented the EdgeOtsu thresholding algorithm, which extracts the edges of features in an image using a histogram-based approach. In using the EdgeOtsu function in HydroFloods, we define the algorithm parameters depending on the satellite and sensors used. And the resulting flood extent maps from EdgeOtsu are these Boolean outputs with pixel values of 1 indicating water and 0 for non-water areas. And then we use the JRC yearly water classification history dataset to then mask out permanent water areas. So then we have just a resulting final flood map. And after EdgeOtsu thresholding, we then aggregated our outputs and looked at the flooding impact over various land cover types in the region. So the next several slides we're going to look at show example flood maps derived from optical Earth observations. Although our optical analyses focused on comparing outputs from each satellite and sensor using the same methods, future methods to combine these outputs can be used. In these slides, we're going to focus on a few sites that were of interest to our partners. Specifically, we looked at flooding in the Alto Verapaz, Sula Valley, and Reserva de Vida Silvestre San Bernardo, and this is displayed moving clockwise. Floods are aggregated by 2 time frames, so a 2-week period combining the events of Eta and Iota, and 2 weeks after the combined events. And we looked at various land cover types, including cropland, forest, and built-up areas when examining our optical and SAR flood map results. And as you can see here again, moving clockwise through these different results, we see a lack of flood detection in, for instance, like a priority site, the Sula Valley, and the after Eta and Iota map there. We don't see any sort of flood detection, and again, that is due to most likely there being cloud cover rather than there being no flood during this part of the hurricanes or following the hurricanes, Eta and Iota. And we'll see also with our Landsat 8 map, flood maps derived here, again, during Eta and Iota, for both the Alto Verapaz and the Sula Valley region, we see essentially little to no flood extent maps here. And again, this is due to cloud cover being present rather than there being no flood detecting using hydrofloods. So again, indicating why using a variety of optical satellites and sensors for these hurricane events to evaluate flooding is crucial, rather than focusing on just one optical Earth observation. So again, we also looked at Sentinel-2 based optical flood maps. And here with the satellite and sensor, just for this part of the case study analysis, we see flood impact in all of our during and after Eta and Iota inset maps for each of these 3 priority sites. Although there is some cloud cover still present, indicating the severity of the flood extent map. So for instance, in the Sula Valley, in the after Eta and Iota image, there are some gaps there in flood extent, and this prohibits us from being able to see the full flood extent and impact after these 2 hurricane events in the region. So looking at the Suomi NPP VIIRS flood map here, we also see some similar patterns in flood extent, although the resolution of these pixels is much coarser just based on the characteristics of using Suomi NPP VIIRS for flood detection. And we also see, notably in the Sula Valley, that there's a lot of gaps between the flood pixels, and a lot of the coastline is still accounted for as flood compared to what we saw in some of the previous results for our optical maps. And then our last optical flood map here, these outputs were derived from using TerraModis in our optical methods here. And again, we see some similar patterns, except one thing to note here, again, pointing to the Sula Valley region, we can see that flood extent here looks a little bit greater than some of the previous slides. Again, that may be due to cloud cover, but also just some characteristics with using these different satellites and sensors for our case study analysis. So again, as you can see through these different example results with the optical part of our case study analysis, that limitations like cloud cover can really prohibit being able to look at flood extent fully for these different case study events. So something to keep in mind when using hydrofloods is to look at both optical flood maps, but be able to also prioritize using SAR as well, which we'll see in this example output here. For our sub-SAR flood maps, we'll be looking at the Sula Valley region in particular. So as you can see, some similar patterns in flood extent for during Eta and Iota and after Eta and Iota from the optical based maps. So some similar results here, but again, likely less overestimation of flood extent here, and also not as coarse of a resolution compared to some of the previous optical maps. So again, we can also see flood extent over different land cover types. So in this region, we can see a lot of flood extent over cropland, and also some flood extent nearby built up areas. And as I mentioned too, it's important to note with SAR, a potential misclassification of flood extent went over built up urban areas in general, so something to take note of when using hydrofloods to detect flood extent. So this final SAR-based flood map we produce differs from the previous ones as we decided to look at the duration of flood using our SAR methods in the Sula Valley. So essentially we wanted to see the extent of flood over a longer period of time to really see which areas are impacted the most from flooding from these two hurricane events that hit the area back to back. So again, we have the Sula Valley here with 1 week of flooding after both hurricane events in this orange color, 2 weeks after is in this green color, and 3 weeks after Hurricanes Eta and Iota, we have this purple color. And again, the dates here are noted as well. So 1 week after both Hurricanes Eta and Iota being from November 18th, 2020 to November 25th, 2020, 2 weeks after, and then also 3 weeks after, ending around early December in 2020. And as you can see, looking at this map, there's a lot of flood extent overlaid on cropland areas and a lot of impact there. And we can see in the purple flood extent that there are some areas that really had persistent flooding, even numerous weeks after these two hurricane events. So again, this really shows some of the variety of applications that can be used from using the HydroFloods tool. So again, you can just look at flood extent for a certain period of time, whether that be over longer periods of time or shorter, and really be able to cater the analysis to your study area and time period, and be able to produce a variety of different maps here, whether it's a side-to-side comparison or be able to look at flooding week by week after these two hurricane events. Now that we went over examples of using hydrofloods for detection in Central America, you may be wondering how to use hydrofloods for your study site. So hydrofloods can easily be applied to your location of interest, either using a GURS engine asset shapefile or using the hydrofloods country VBox function to specify your country of interest. Next, you should be able to specify the study period. So this goes hand in hand into calling in the different Earth observation data sets to the script. So specifically when calling in optical or SAR imagery using hydrofloods, you note which Earth observation you'd like to add to your script, and then you'd use the defined study area geometry, whether that be, again, defining the country of interest or using your own shapefile to specify that geometry. And then you add in a start time and end period as well to really call in the data set and filter it automatically to the study period and area of interest. So this helps the user get the imagery just for, again, the study period rather than calling in an entire image collection with several dates. So also helping with just the efficiency of collecting this imagery into your script. And again, these inputs can easily be adjusted to your study location and period to help facilitate your flood monitoring efforts, again, for your region of interest. In our case, we then also identified areas of interest based on partner input. So again, really just focusing on your study area of interest. And we process SAR and optical imagery using HydroFloods and Google Colab. So again, following the same methods of pre-processing and using EdgeOtsu, you can achieve similar results in your study area. Although we use EdgeOtsu, there are some other thresholding techniques also available in HydroFloods and are documented as well. And additionally, you can easily export your imagery from Google Colab and be able to work in other software as well, and overlay certain land cover types, perform zonal statistics. So a variety of different methods and applications available from using HydroFloods. So to conclude the application of HydroFloods for flood monitoring efforts and through this case study analysis of examining Central American flood extent maps following Hurricanes Eta and Iota, we observed similar flood patterns and extent during and after the two events using both SAR and optical imagery. Again, HydroFloods provides several Earth observations, either SAR or optical, and can be used for your analyses in your study area of interest. We also saw that Hurricanes Eta and Iota deposited more than 1,400 millimeters of rainfall, mainly on the east coast of Central America, with Guatemala and Honduras receiving the most rain, and again, helping us identify where to look at flood extent following these two hurricane events in Central America. And we also generated a tutorial allowing users to replicate these analyses, again, for your study area of interest. So again, lastly, just noting some of the limitations with just examining flood extent in general, which will be applicable when using hydrofloods. So although we used optical imagery in conjunction with SAR, limitations with optical imagery such as excessive cloud cover during these hurricane and after these hurricane events, it really inhibits the ability to look at flood extent fully. So again, SAR can come in and be able to detect flooding in areas dominated or detect areas with excessive cloud cover, although it's important to note limitations with SAR. So again, as I mentioned, built-up urban areas can often be misclassified as flood, as well as it can be difficult across other land cover types. So again, using the combination of SAR and optical imagery through the use of hydrofloods can be extremely helpful in flood monitoring efforts. It's also, again, important to note the limitations with long revisit periods between satellites, so contributing to gaps in data along with the cloud cover issues with optical. And then lastly, detecting and classifying flood water using satellite imagery can be confused with other land cover types. This includes other water-based land cover types, including pond aquaculture, as well as, again, urban areas. So it's important to keep these limitations in mind when applying hydrofloods for flood monitoring efforts, or in general, just using optical and SAR-based imagery to examine flooding. Thank you again for allowing me the opportunity to discuss a bit about hydrofloods and the application of it for your study area of interest and through this case study analysis in Central America. I just would like to have a huge thanks to everyone at NASA Develop and all of our advisors, our fellow and partners on this project. Again, a huge thanks to everyone working on this project and the chance to discuss hydrofloods and the application of it for flood monitoring efforts.
Thank you so much, Caroline, for that wonderful, very informative presentation about hydrofloods application. So far we have looked at observation-based flood monitoring and mapping tools. In next part, we are going to focus on flood modeling. So we will briefly see major approaches used for flood modeling and then have overview of selected flood models. There are two broad groups of flood modeling approaches. The first one is empirical statistical modeling technique, and that is based on observations. They could be in situ observations, remote sensing, or combination of both. The second approach is hydrodynamic modeling that can have 1, 2, or 3 dimensional representation of water flow in an open or closed channel. And these type of models include hydrologic and hydraulic models. Overall flood modeling and management, they use both hydrologic and hydraulic modeling and also use sediment transport models for analysis. So let's see what the differences are between hydrologic models and hydraulic models. So hydrologic models, they are based on circulation of water through the hydrologic or water cycle and quantification of runoff produced by precipitation. So it deals in a watershed where all the water components are looked at, including precipitation, evapotranspiration, infiltration, groundwater, and surface runoff and stream flow. So that's basically watershed level water cycle processes are modeled here. In hydraulic model, the approach is that the mechanical behavior of water in open or closed channels is represented. It provides water flow and depth as water moves from one point to the next in a channel, and that in addition to information about the channel itself can tell us if there is any overflowing water outside the channel, and that would be the flood part. In general, hydrologic flood models, they're used for understanding water movement processes in a watershed land atmosphere system as shown in here. provides an estimate of runoff in response to rainfall. Not all runoff that is produced goes into river channels or streams, and hydrologic models they partition runoff using either water balance in a watershed or using rainfall runoff relationship for that watershed to see how much runoff actually goes into rivers or streams. And that depends on land cover, terrain, and soil moisture condition of the watershed. Inputs for hydrologic models are rainfall and other weather parameters, watershed delineation and terrain information, land cover, vegetation types and canopy information, and soil characteristics. So all these inputs help in resolving water cycle within watershed. Hydraulic models, they are used for getting water flow velocity and depth in streams, channels, and other surfaces for mapping flood extent and for mapping flood risk analysis. For example, FEMA uses flood risk analysis and mapping based on hydraulic model. For a simple hydraulic model, these inputs are required. First of all, cross-section geometry and hydraulic structure of river channel system, energy loss coefficients due to frictional loss in channels due to channel roughness, water surface elevation at the most downstream cross-section. So details about channel cross-section and elevation are very important in the river channel system. Also required is peak flow discharge for these channels. Both hydrologic and hydraulic modeling are required for flood mapping and flood risk mapping at watershed level. Remote sensing observations are routinely used for inputs such as weather and precipitation data, digital elevation, and land cover. As shown here, NASA Earth observations from several satellites are used for flood modeling, such as MODIS, Landsat, Sentinel-1 and 2. They provide information on land cover. GPM provides information about precipitation. SRTM has elevation data, and SMAP has soil moisture information. Calibration of flood model parameters is necessary, and it's usually performed using historic floods on streams where in situ observations are available of discharge, flood flow, and elevation, water elevation. And so model outputs are compared with these parameters for calibration of the models. This brings us to examples of open source flood models. If you search the literature, several regional or customized flood models are there. We are going to talk about two very widely used flood inundation mapping and watershed river basin scale models. First one is US Army Corps of Engineers Hydrologic Engineering Center's River Analysis System, or HECRAS. And the other one is the Soil and Water Assessment Tool, or SWAT. Both these models are used not only in the US, but everywhere they have been adapted and calibrated for regional use. So what we're going to do is talk about HECRAS first, and then look at the HECRAS website to see how this model software can be downloaded and work with it. There are tutorials online also. And we'll do the same for SWAT after that. So let us start with HECRAS. It contains the following river analysis based on geometry and hydraulic structure of channels. It can be used in 1 or 2 dimensional, steady or unsteady flow simulations of water surface profile. It can be used for getting movable boundary sediment transport computation, and also it provides one-dimensional water quality analysis. So based on water surface computation, flood can be mapped using HECRAS. There is an extensive spatial data integration and mapping system, or HECRAS Mapper,
that allows to integrate data and visualize data as well as flooding information. So output can be viewed using this mapper as well. So what we're going to do is just look at the website here, the HECRAS website. This is the Army Corps of Engineers website for HECRAS, and it has different features, what is available here. So hydraulic analysis, there is data storage and management, graphics and reporting. So you can download this model for Windows and for Linux. So latest version is 6.1, I believe, and 6.3 for Windows. So you can use this website to download and install HECRAS on your own computer and run it. There are demos and there are documentation available. Because there are tutorials and demos available for HECRAS. Right now we are not getting into that, but this is for your information that you can download, go through the documentation. There are known issues, and then there are trainings available for HECRAS, starting from installation all the way how to run it and analyze data. So there are guides and there are reference documents. So this site has a lot of information about HECRAS, and you can go through tutorial to learn more about how to download, install, and use HECRAS, what kind of inputs are required, and how to analyze HECRAS output using HECRAS mapper. Next, we are going to look at SWOT model. It's a Texas A&M University developed model. There is a group that is developing and testing SWOT there, but there are many groups worldwide and there are many applications of SWOT. There are annual workshops where everybody using SWOT comes together and shares their applications. So SWOT is a watershed to river basin scale model. It simulates quality and quantity of surface and groundwater. It predicts environmental impacts of land use and management practices and predicts impact of climate change. SWOT is used for assessing soil erosion prevention control, used for non-point source pollution control, and 1 and 2 dimensional steady and unsteady flow simulations of surface water can be done with SWOT, which is used for mapping floods. So let us look at SWOT website. From Texas A&M University site, here you can have software, documentation, data, the information about workshops and conferences, publications. There is also SWOT support. So it is really a very well used model. You can get a download SWOT model executable, and there are interfaces with ArcGIS, QGIS, and SWOT Cub is the sensitivity analysis and calibration of SWOT that is required if you want to use it for your own region. So if you look at software, here is where you will download this data. Also, you can do output analysis by using SWOT Check and SWOT Output Viewer. There are community tools which are RSWOT, and there is SWOT toolbox with a lot of information. So the idea here is that we want to point these models out to you, both HECRAS and SWOT. They have a lot of resources. They have online tutorials and trainings that you can go through for your own region, how to download, how to install, how to get input data, how to run the model, and how to then analyze data. Also calibration of these models. There are steps involved in both, and they're available from their websites. So these two open source models we wanted to introduce for your information. So there is SWOT Online, that's application of SWOT using NASA data. SWOT Online was developed for customization, execution, and visualization of SWOT input and output data. Particularly, it's a web application development tool for climate data retrieval. So it accesses, fetches, extracts, and reformats NASA climate data for SWOT input. And you can look at the links for more information. So an example for the lower Mekong River basin is available using SWOT online, and contributor is Ibrahim Muhammad. You can look at SWOT online home, and again you can look at data, documentation, there's general manuscript, and there are scripts available. So this is specifically using NASA climate data to run SWOT and to look at output for different climate scenarios. So finally, we want to talk about global land surface and hydrology models. We talked about HECRAS and SWOT type of models, which are used for small watersheds or small river basins. But there's a class of global or regional models which are available based on land surface processes and water balance approach, which can be used for much larger than watershed level. So larger river basins or even country level, they can be used. So these models, they utilize weather information for forcing and calculations of runoff at model grid points. And then a routing model is used to distribute runoff into stream flow. So NASA has land information system that is shown here. These are hydrology land surface model. They use water and energy balance. So inputs are given such as topography, soil properties, vegetation properties, weather conditions are provided including rainfall, and then observations of soil moisture, snow, temperature. These are inputs to land information system. And then river network information is also provided. So HIMAP is a routing scheme. So LIS output of surface runoff and base flow is given to the routing model, and river network information is also provided here, including width, depth, length, slope, etc., and drainage conditions, of course. So using all that information, HIMAP then provides water discharge, water level, flow, velocity, flood extent, and evaporation from floodplains, etc. So this is the model that we are going to look at next week. So what we're going to do now is go to question and answer session.
Hi everyone. Sorry about some technical difficulty here. I think that there is some glitch here between our audios and video slide presentations. Here is what we were talking about, that there is a class of global or regional models, global land surface and hydrology models. They are available based on land surface processes and water balance approach. So SWOT and HECRAS that we just talked about, they work on small watershed or small river basins to have much larger the area than what your watershed or a larger river basin. The class of model used are global land surface and hydrology models. These models, they use weather information for forcing a land surface model, and they calculate runoff at model grid points. Then this runoff is routed in river streams using a routing model. So here is a NASA land information system model. That's a land surface model. It uses inputs from such as topography, soil properties, vegetation, also meteorological parameters, and soil moisture, snow, skin temperature, etc. When the land surface model runs, it provides surface runoff and base flow, along with river network parameters such as river width, depth, length, and slope, drainage area flow direction and floodplain depth, combined with this runoff information, this routing model here, that's HIMAP, that provides water discharge, water level, flow velocity, flood extent, etc. for river channels. So this is the model that we're going to talk about and present next week. So how land surface model can be used along with the routing model to get flood information in channels. So with that, we're going to go to the question and answer sessions. While you type your questions in the chat box, we will address them in the order they are received. I just kind of want to summarize that we went through flood observations tool using optical and SAR data. So long-term tools are MODIS-based, flood mapping. There's also Flood Observatory River Watch based on microwave radiometry that also has a long time series. Then there is GDAX that provides information not only just from remote sensing, but from variety of sources, in situ and models. And then Caroline presented a case study using Hydra floods, which is a newer model that provides flood information based on SAR and optical data. We saw a case study for South America. The Hydra flood code can be downloaded and trained for your own region. That there's a little bit of learning curve. And so for this introductory training, we have not included that, but this is more for your information so that you can get familiar with that. And then we talked about flood modeling approaches. We had two specific models we talked about, HECRAS and SWOT. Both are open source, and a lot of training and tutorials are available for those two models. So, and there's literature out there. People have used both those models. They're well tested and validated. So you can download the code and train for your own region. They both have a large amount of resources to visualize data as well. So that's where we ended today. And next week, we are going to present this land information system and HIMAP routing routine, how that works for flood detection. That can also be used for flood prediction. So we will go to the question answer session. Before that, here is our contact information. You can send us emails to either me or Caroline or Sean McCartney. Here is the training webpage, and this is the RSET website. That we are also on Twitter, so you can check us out. We also will ask you to check our sister programs, Develop and Surveyor both. So with that, we'll go to question answer session and try and address all the questions. Thank you. Okay, so here are the questions. We will address them as many as we can. Otherwise, we will post them online if we cannot get to all the questions. Okay, so question one is, do any of these databases work better for detecting water under vegetation? So SAR has capability to detect water under sparse vegetation, and hydro floods, so that can be used in your region, and you may be able to detect vegetation flood under vegetation. But here is a paper that is useful for more information on that. It talks about how SAR can see under vegetation, especially when it's sparse vegetation. We will also check with our RSET SAR expert and let you know about that. The second question is, will ARIA eventually have an in-window data viewer? So we are not sure about that. We will check with ARIA group and let you know if they're planning that, or we can also suggest them that if they haven't planned it, can they consider? So there's a question, can we monitor volcanic lava flow mapping too, like flood mapping? And I think that's a really good question. And this is what I have not looked at lava flow using satellite data yet, but my hypothesis or my conjecture is that when lava flows over, say, a dry surface or any surface, of course, the land cover change should be detected by imagery, satellite imagery, if it's high resolution, high enough resolution is there. So you should be able to see that something has changed over surface, but to to discriminate whether it's really flood or lava flow, I think thermal imagery might help, because lava flow would actually look very hot and it would show up in thermal imagery. So that's my conjecture on that. Question 4 is, do you apply an additional mask over urban areas for S1 data? So I don't think we have talked about that in our SAR webinars. And when Caroline, if you have, when she joins us, she can tell us if Hydra Floods has any mask for urban areas. But there is a paper I saw that it talks about using interferometric SAR coherence, and that might help in better detection of urban flooding. If there is LiDAR information available, that also helps. So you can check this paper out. They have used Sentinel-1 data 6 days apart, and then they have tried to do coherence analysis, and that helps in urban flood detection. So for question 5, I would wait. Is Caroline here? So we'll get to question 5 later. So question 6, is it possible to use Hydra floods for flood prediction and possible response intervention? So this is based on observation. So prediction is not possible with Hydra floods. It is more like sensing floods in near real time using optical and SAR data. So, but for rapid response, it should be helpful, because you can get information about flooding when it's happening. It's possible to respond interventions at small scale resolution, cities and neighborhoods. So the resolution here is 20 to 30 meters. It is possible to really look at communities or urban areas in this. Flash flood, I'm not really sure, because duration of flash floods in response to heavy rain is short, and if you do not have satellite overpass right during that time, it is difficult to see. Yeah, there is also a good question. Caroline was showing some nice daily precipitation analysis in Central America. What could be the challenges to use hourly assimilated data for precip and soil moisture for early warning detection of damaging floods event? So yes, that has been happening. People use even cloud resolving model with input from assimilated data every hour, and then you can have early warning based on that. So models like WRF, they are used like that. You can use if you just want to use hourly precipitation soil moisture for warning, you can do that too, depending on the resolution of the output model. So I assume that this is about models. How can we generate the NET or flood maps using these products? Um, so if you're using models, they do have forecast capability, because both, if you use forecast model, weather forecast model, then you can predict, use either HEC-RAS or SWOT with that, or use any land surface model with that in predictive mode, and then you can get flood forecast. How well do, this is question 8, how well do your satellite flood maps compare with those from hydrologic hydraulic model floods? What products did you use for your validation, and how do you account for satellite missed periods during active flood events? So that's a good question. Like for the satellite flood map, validation is not done with hydrology or hydraulic models. It's the other way. Models sometimes use satellite-based data for validation. So for validation, generally it is the in situ data that are used. So if there are stream gauges or rain gauges, so those are used. So rain gauges can tell you that yes, precipitation used was correct, and then stream gauge data are basically used for validation of satellite-based flood model. That when you see flood peak in certain area in satellite pictures, and at the same time stream flow also shows that you can say that yes, model satellite pictures did show that flooding correctly, somewhat qualitatively, but it does confirm. Now when the satellite is not monitoring right when the flood is occurring, such as in flash flood, it is then it's gone. You really can't see that. So that is not part of the satellite flood map. You can only get a flood map when satellite can see it. So what helps is there are two ways to do it. One is if you have a geostationary satellite where you have very frequent observations, then you can monitor almost continuously, and then you can say whether flood is going on or not. But SAR data are not available like that. So if it's very cloudy, you probably won't see the surface. And in this case, is only statistical methods they infer to flooding. So it's a complex problem, but yes, there are some ways around that. Question 9 is there a flood mapping algorithm by Hydra Floods that only makes use of SAR data, or are SAR and optical used together by default? I believe if you look at the Mekong site, and Caroline can answer this better, but if you look at the Mekong site, they have just SAR-based flooding, they have just optical-based flooding, and they have merged products. So yes, I believe that they have algorithm that can just use SAR. And in the presentation, there is a reference to an RSET training that also shows how you can just use SAR for flood detection. Question 10 is there any technique to identify the number of vulnerable population of flooded areas captured by remote sensing? So there is NASA CDAC has population density maps. If you combine that with, if you look at that with flood map and low-lying areas from terrain, you can identify vulnerable population based on that. So you have to use that additional information. So CDAC does have population density available. In the US, Census Bureau also has population information. So combining flood maps with population maps along with low-lying area map or elevation map can help identify vulnerable population. Question 11. During a flood, is it possible to quantify the amount of soil lost through the turbidity of the flooded water during a flood? Okay, and is it also possible to determine along the flood which parts receive the highest amount of sediment? So there are sediment flow models. That is not our expertise, so cannot give you a lot of detail, but we'll try and provide some references. So there are sediment flow models that can tell you that how through turbidity that how much uh, soil is lost, and also determine which part receives the highest amount of sediment. If you have multiple streams, which streams are bringing more sediments? If that's what you mean, I think there are models which are trying to address that. Question 12 is, can we monitor salinity in seas with the flood monitoring tool? I don't think you can monitor salinity. You can see where the fresh water is getting into the seas, and then maybe you can identify areas where salinity is changing, so decreasing. But to quantify salinity based on just flood monitoring tool would be difficult. So using hydra floods, this is question 13. Using hydra floods, why not use ground truthing points for flood mapping? Okay, we'll wait for Caroline to help us with that. Question 14 about hydra floods. Is it possible to download any information from the portal to use in other software, maybe as a VMS service or another? We will check with HydroFlood site and let you know. But you can download the software for sure. And then you can use it in other software, I mean. Okay, question 15. Why the assimilation of SAR and optical data? What is the purpose of this? So optical data, when they are looking at surface, they are actually affected by clouds. So if there are clouds present, you cannot see the surface. So if the flooding is going on the surface, and there's rainfall going on at the same time, a lot of clouds are there, the optical images will not show anything. It will just show clouds. But SAR, being microwave, can see through clouds, and so that it can see the surface. So combining both is useful because first, optical data are more often sometimes. Also, it has larger coverage, and SAR can then see through clouds. So combining them has strength. Question 16 is DEM used to obtain a better results in HydroFlood's algorithm or in other flood tools you mentioned? What would the advantage be? So yes, DEM is definitely used in all of them. So MODIS-based flood tool and HydroFlood, they all use land cover and terrain. For optical data, sometimes like if you have shadow due to topography, that has to be corrected. Otherwise, there could be, it appears like flood. So for that, it is used in optical imagery. And in hydrofloods, I believe it is the same. So interpretation of your flood map helps when you have DEM information in there. So question 17, what could be the best option to use for monitoring or assessing the flood impacts, especially in case of cloud cover during the flood period? So if you have SAR data available at the same time, you can see what's going on below the cloud cover. Other than that, you really have to closely follow precipitation, say, and locate where high precipitation is, so that you, based on past flooding information, then you can have some statistical methodology that tells you that where there may be more flooding, and where help may be needed, and assess impact there. So that is the only suggestion I have, that below clouds, if you cannot see flood while it's occurring, then you have to use other flood proxy data, such as precipitation and knowing terrain, knowing where past impacts were highest. You can come up with a scheme where flood impacts are and how to deal with them. Question 18 is, can we use hydrofloods to monitor debris flow? So debris flow, I'm not sure, but if you look, if the river channel is wide enough, optical imagery, when it's cloud free, can show when turbidity has changed. So that can tell you whether, because of debris flow, what has changed or where it is, but I don't think you can actually see the flow. Question 19. How can I model floods using HEC-RAS in ungauged basins? Any suggestions? I mean, when channel geometry and other data are not available. So that is a good question, and I will get back to you. I will provide that answer in our website, because I know that for ungauged basin, SWOT has some solution. HEC-RAS, I'm not sure. So if you don't have hydraulic information available, I'm not sure how HEC-RAS works. So we need to check that. Question 20 is, which matrix and or validation procedure is recommended the most for satellite derived maps validation? Yeah, so I would say that so flood map, if you want to validate, you have to have some stream flow data nearby. That's the only way you can be certain. But we'll give you more details on that. So question 21 is, do you know if there is any resemblance between HYDRAFlood's algorithm and SNAP algorithms? So I don't know much about HYDRAFlood's algorithms in detail, so we will have to find that out and get back to you. Can we use HYDRAFloods to monitor flash floods on a daily basis? I think you can see like Weir's is used, Landsat is used. So you do have some daily data from WIRS, but flash floods can be so quick. I think it would be difficult to get those from hydra floods. If I edit my own software, where is your API that I can use to download a large amount of data? So question 23, can you be more clear? Is this about the Python API that Hydra Floods has? Or which API are we talking about? Question 24. Coastal estuaries are complicated because of the combined effect of regular daily tides and downstream riparian flooding. Will this course cover such circumstances? So next week, when we look at HIMAP, we can bring this question up. This is not really specifically covered in this course. Question 25 is, can we apply this to measure melting of glaciers? Optical imagery is used to look at melting of glaciers, so it is possible, yes. Question 26 is, how valid could the satellite data be without in situ data? Can researchers use the satellite data without in situ data for validation? No, in situ data are important for validation. So if you look at NASA missions, along with each mission, there are field experiments for validation, as well as there are aircraft flights in certain areas. So there is some form of validation done for each mission, but it's not everywhere. So it is difficult to see accuracy of satellite data if you don't have any other means of validating. In that case, what you can do is take the difference between satellite derived products, say, and that change, may be more meaningful than just actual parameter that you get from satellite. Question 27 is, what tools might be the best choice to analyze how flood extent and duration has changed over time? So I don't think there is one tool that can tell you. Long-term flooding information is available from MODIS. Landsat also can be used because it is a very long-term data set, and it has been used to look at surface water changes. So you can use any optical data and look at flood extent for sure. Duration is tricky because of data are not continuous and there are cloud covers. So optical data probably, even if it's daily, we cannot see all the time. So duration of flooding, how it has changed, you can see only from like stream gauge data. That's the one way of doing it. Or you can use precipitation or other data sets as proxy to see duration. Extent you can definitely see from optical data. So it's a combination of tools or data sets you might have to use. Is there a way to determine flood inundation depths? So when you have a routing model, like we're going to talk about next week, you have that information. Also for using hydraulic model, where you already know channel depth, you can, and then you also know surrounding areas, you can gauge flood depth. But routing model should say that, yes. Is there any way to integrate machine learning or artificial neural network flood modeling and hydra floods for mapping? So it is certainly possible. It's a research question. It's we're not doing it, but it's certainly possible that you have uh, multiple data sets and algorithms, and if you can combine it with machine learning. Can satellite, this is question 30, can satellite data quantify the amount of water in flood affected area? So that satellite data along with hydrologic model can do that. So not just from satellite data, but if you have all the water cycle components, then combining remote sensing data with hydrologic model data, you can gauge quantity or amount of water in flood affected area. Uh, how we can forecast flooding. So you can use HECRAS or SWOT kind of model where you provide inputs from forecast models, weather forecast models, and that way you can have a flood prediction. This is question 31. Question 32 is there a way to conduct flood risk assessment using DEM and LULC? I believe it's possible, yes. We will try and find if there are any studies like that, yes. Question 33 is, can satellite data determine the speed of flooding water? So again, if you use hydraulic model, then flood velocity or flow velocity is the output of the model. So satellite data using as inputs for hydraulic model, that can then lead to flow velocity. Okay. Question 33 is, what are the limitations of using SWOT? So that is not a straightforward answer, so we will get back to you on that. We also have Caroline with us. Caroline, thank you for your presentation. And there is a question that we were hoping you can help us with. Question 5, I believe. If you can unmute.
Yeah, absolutely.
Yeah.
Awesome. Yeah, I'm glad that I was able to join today. So I'm just seeing the question now. So asking about the Edge Otsu thresholding method. So I can touch into this a little bit, but I definitely recommend there's some papers from essentially like one of the main developers of the HydroFloods tool where he goes into explaining the different thresholding techniques, there being Edge Otsu, and another Otsu thresholding technique. So he kind of goes into the pros and cons in this paper, which I'm happy to follow up with on like any of the DOI links, anything like that. But essentially, it's sort of like an automatic thresholding technique where you can apply sort of input parameters into hydrofloods. sort of like an initial threshold value that you think may help separate water and non-water. And then essentially like the thresholding algorithm will go through automatically and try to have an official like threshold separating and classifying those two. I do think this paper that I'm referring to and can follow up with will have a more detailed explanation though on like the different advantages of using these two different Otsu thresholding techniques, especially like why at least they prefer using the edge Otsu thresholding in hydrofloods. So I'm definitely happy to follow up with that paper since it'll go into a lot more detail.
Okay, then also I'm trying to put a link here from HydroFloods that may be helpful in looking up the information. I'm putting it in the chat if you can. Okay. Then there is question 6 also, I believe. Yeah, that's been answered. So, okay. If you have any more questions. Question 35 is, can LiDAR data be integrated with optical and SAR for better flood assessment? Yes, I believe they can, and especially if you are using flood modeling, then LiDAR helps too. Question 13 is, using hydrofloods, why not use ground truthing points for flood mapping? Caroline, do you have?
Yeah, I can jump in here. So I guess ground truthing points could be used for hydrofloods if you're looking to like validate flood versus like non-flooded areas. So you definitely can do some sort of like validation if you would like with ground like truthing points. If you have that sort of like in situ data to be able to do that. So I'm sure you can do some sort of validation efforts if you would like to. In the project that I presented the overview on, it was a 10-week feasibility study, so we can get into any like extensive validation efforts. But definitely, I think ground truthing could be incorporated into like a hydroflood-based analysis.
Question 14 also, Caroline, is it possible to download any information from the portal to use in other software, maybe as WMS service or another?
So I'm not too familiar with WMS service or like that example, but at least with hydrofloods, since it's using Python, you can incorporate different packages if you'd like to. So hydrofloods is based on the Google Earth Engine JavaScript, or not JavaScript, Python API. So you can incorporate other packages that you'd like to in Python. So if you have certain softwares that have like a Python-based API, you could also try to incorporate that into the same script as well. To my knowledge, I don't believe there's any way to incorporate hydrofloods unless into other software, unless that software has a Python element to it.
Question 31, I see it's not answered here, but we did talk about it. You can use SWOT or HEC-RAS or any other land surface model with inputs from weather forecast model. And then that will give you a predictive part of, can give you forecast flooding.
Hi, I'm seeing question 21 here. So do you know if there's any resemblance between hydrofloods algorithms and SNAP algorithms? I'm not too familiar with the SNAP algorithms, so I probably can't speak to this too much. But if whoever wrote this question, if there's sort of any, or if anyone knows more about the SNAP algorithms, I could try to talk about it further. But currently, to my knowledge, I'm not too familiar with that other algorithm mentioned, so I can't explain the resemblance between the two at this point.
So there are no more questions. Then we thank you for attending today's session. We will have one more session next week on 21st of September at the same time, and we'll talk about LIS and HiMAP routing model at that time. So thank you for attending today's session. Also want to thank our RSET team, especially Caroline Williams from NASA Develop for her presentation and information about HydroFlux. From RSET, I want to thank my colleagues Sean McCartney, Selwyn Hudson-Odoi, Sarah Kershell, and Jonathan O'Brien for their help with this webinar. So thanks everyone, and thank you everyone for attending today's session. The material will be available online. Again, we apologize for the technical difficulty that there was a mismatch between some audio and video. We'll make sure that when we post this on website, it's all taken care of. And we will see you next week. Thanks, Caroline, again for your time and help with this.
Thank you. Yeah, glad to be here.